Thank you all for coming. Ron and I are blown away by how many people decided to come and from how far away people have decided to come, so thank you very much. We have many states covered here. Farthest continental drive was, or flight was from California, but the prize goes to Xi Ying, who came from Beijing, China, the Chinese Academy of Sciences, so she gets the prize for the longest distance. Thank you for coming. I hope we'll have a couple of 15-minute breaks during the course of the day for networking and talking, and hope you'll get a chance to meet with her and talk about her research program. She's working on drought-tolerant wheat just outside of Beijing. Let's start with what we're going to be talking about today. Today is a workshop, and it's an interactive workshop. And during the course of our tours, I got to hear from the people that are coming into this workshop about the types of stuff they're really hoping we're going to cover. And that list was so long, it was kind of blowing me away. So I don't know if we'll cover everything that everybody is hoping for, but obviously this workshop is addressing some kind of a pain in our industry. There's a lot of interest in it, a lot of people wanted to come, and so we're going to do our best. Now this is an interactive workshop. The professors have agreed, but one of the professors, who's an early presenter, is not here yet. I just saw that, so I might have to improvise. Oh, is that right? Okay. Well, we'll see. But this is going to be interactive, and I think we get the most out of it by just going ahead and asking questions. Please don't be embarrassed that your question is too simplistic. That's why everybody's here. I consider this to be like a jazz performance. We have invited a bunch of very talented people to come here and present. They all have their unique talents and their unique perspective, and they're going to be improvising with us. But the audience is part of the performance. So by asking you questions and directing them, we hope everybody gets maximum value from this particular workshop. So what we're going to try to do today is the first question is, why are we doing experiments? And Stefan, I don't know if I got this from your thing or not, but I thought I'd do it. So there's kind of a pyramid of why you want data, from you just trying to describe something to predicting, explaining. You might want to do simulations, and you might want to do optimization. So many of the companies here actually would like to do optimization. You know, what's our dose rate, our mixtures of surfactants and active ingredients, and how do we keep our bugs alive for a maximum amount of time. But you can't just do that with one small sample size experiment. So you need, everything has to fit together, come together, lots of different knowledge, and you might have to leave statistics to develop linear, nonlinear models of what it is that you're trying to understand. So it requires a lot of work to move up that pyramid, and we're not going to be strictly limiting ourselves to just the first base of the pyramid. What happens is, this is all about small sample sizes. So what happens when you take just a few data points and you try to come to conclusions? And this series of graphs here are just what happens to your knowledge base as you start adding more data points. So the first data point we happen to take, which is a light blue star up there, it turns out that one measurement was all I really needed, because it turned out to be very close to the mean. And that's one of the things with statistics. How do you know when to stop? Why would I spend more money if that first one? And I didn't set this up. This is just random data, real data from our system. So then the red one is the next data point. It was over here. And then this is a curve that kind of approximates the data from a normal type of a situation, et cetera. 3, 4, everything seems to be lining up here and really nice standard deviation, and all of a sudden we get a point over here. Everything skews down, starts spreading out, our standard deviation goes out, and we add another point and it starts coming back in. And this is what happens. We come in, we go out, things happen. When can we stop? In agronomy, I heard last night that the magic number is 4. When I was at one of the corporate meetings, the magic number was 3, I think. When I went to one of the big genetics company, the magic number was 192. So where do these numbers come from? That'll be a part of our discussion, and are they valid? So this is, we're going to get to the point sometime midday where everybody will be able to look at this and understand everything that's on this particular graph. These are 2 treatments. We have controls in blue. We have product in red. That looks like beautiful graphs of normal distributions. Got standard deviations that are comparable. This is with 8 plants. We can calculate 95% confidence levels. So we're going to get everybody up to on the same page about all of the mathematics and how you get to that particular point. But then you have this beautiful picture, but what's the reality behind it? We're showing beautiful normal curves, but was the data that gave us the standard deviation and the mean that we used, was it really normally distributed? And how do you test and verify that it was normally distributed so that this is a valid graph? Dr. Van Zatten will tell us that that's not really that important. It's more important to take a look at the residuals. Okay, residuals, we got to talk on residuals from another person. So we're going to hear about residuals and the role residuals play in all of this. One of the ways to take a look at normality is to do some charting and try to simplify the way you're looking at your data. This particular approach is a histogram. You just take your 8 data points and you plot them in a histogram. And then the orange lines, this is the mean and the standard deviation from your statistical analysis. And then you look at those points and say, does that distribution seem reasonable as an approximation of normality? I don't know about you, but I don't know. I don't know how good that is to normality by looking at graphs. Another approach is to do the point probability where you have an ideal situation in your data and you plot them against each other, and if they're on a straight line, you got perfect normal data. But how much can you deviate? Is this close enough? Is that close enough? If you got points that are real close together, at what point do you have to reject some of this? This is the bar on the 95% confidence level as a function of number of data points. And this is the T-statistic, which we will be discussing and developing. And the T-statistic kind of comes down and says if you start adding more and more data points, you're not gaining that much more. But when you combine it with your actual data points and your standard deviation as you start accumulating data, you find the confidence level is not monotonically decreasing. It just so happens that your first 6 points or 5 points brought you down to here, and if you stopped here, you'd be making some kind of conclusions about your 95% confidence levels. But just by adding a few more points, it turned out that those points were a bit further out, and things spread out. So when do you know when to stop? And what murmur did I hear from over here? Dr. Van Zatten is going to talk about all the conceptual and other mistakes made in statistics. He's already shaking his head from my graph, so we're all going to be educated today.